we're going to do, if we have enough time, we'll do both the coaxial capacitor and the spherical capacitor. And we're going to talk a little bit about why spherical capacitors are even discussed, but mostly I want to focus on right now the coaxial capacitor. So to kind of start us off here, remember that capacitance is defined as Q over V. That's how we define capacitance. And a capacitor is a device that has capacitance. So in order to determine the capacitance of a device, you either build it and you apply a voltage and see how much charge is on it, which is nearly an impossible thing to do, or you do what we talked about in class. You assume it's charged to Q. You find the electric field. Due to the charge. You find the magnitude of the potential difference between the plates. And then you plug it back into Q over V. When you do those things, when you do all that correctly, Q should cancel out. That's the whole thing. You should be left with something that's based on the geometrical shape of the object. So we're going to do right now the cylindrical capacitor. Now, it's hard to draw this, so I'm going to do my best here. But remember that if we're dealing with a cylindrical capacitor, there's going to be the inner core shell, which doesn't have a zero thickness. It has some thickness, because you can't make something zero thickness. So we're just going to say that it has a radius equal to A. And we're going to say that although this is going to represent the length of that core, we'll put L here for the length, we're also going to say that L is much greater than A. We're then going to surround it with another cylindrical shield, and this is going to be the outer shell, something like that. And we're going to say that it has radius B. So this is trying to look straight on at it. I'm not trying to make some 3D picture. And I'm just having the end stick out a little bit so that we have some differentiation. But can you kind of imagine what we're talking about? Because if we looked straight down, like at it, like we just turned it on its side. Love days like today. We get something that looks like this. It was a mess. College Board went down nationally this morning. So it took a long time for all that to get together. All right, so this is our cylindrical capacitor. We'll move those things off to the side, and we're going to go through the process. The simplest process is to say that we are going to place a charge of Q all along our central piece there. Now, truthfully, we could say it's either a very thin shell, or we could say it's a solid core. It won't make any difference, because we're only interested in the electric field between the inside and the outside, the electric field here. So all I really want you to recognize is that we can treat this with linear symmetry and say that the charge per unit length is going to be Q over L. By design, the outer shell will have charge negative Q because the charge for the inner shell comes from the charge for the outer shell, or vice versa. We move charged particles from one to the other because of an applied potential difference. We're doing the work backwards. We're saying the charge exists, and we're figuring out the electric field and the potential difference from there. But the idea is that we took charges from one shell and placed it on the other. That's what we're saying we did. Now, we assign Q as the charge. The next thing we do is we find the electric field in the region of space where the capacitance is taking place, where where the space is between the two. So we have to choose a shape, and that would not be the right one. Let's choose a cylinder itself to fill this space. Because again, step 2 is for us to find what the electric field is in the region of space between the inner shell and the outer shell. I'm going to choose a cylinder that has height h and has radius r, and r is going to be between A and B. I don't think I have to spend a lot of time doing this part because we've done this a ton of times before, and you should have an expectation of what the answer is. So remember, we're going to apply Gauss's law. We're going to say find the Q enclosed, and then we're going to find the flux, and we're going to put those two things together. I think the Q enclosed is the easiest. It's going to be H times lambda, which for this part of the problem is going to be H over L times Q. And that'll be our Q enclosed. Any question about that? All right, so next we're going to take a look at our flux. And a reminder that there are 3 surfaces, so E dot dA plus E dot dA plus E dot dA. This represents the flux through the sides, top, and bottom. Again, I'm going fast because we've done this before, like several times. So if you have a question, stop me. But remember, we believe the electric field is uniform in this region, and we believe it is perpendicular to the inner core of the wire, which means that there is no flux through the top or through the bottom, and the only flux we have will be through the sides. That all still good? And for this particular shape, the electric field times the area of just the side will be 2 pi r h. Gauss's law is Q enclosed equals our permittivity. Now, I put, permittivity not, but the truth is we could fill the space with something. As long as the space isn't charged, we can just say the permittivity and understand that there could be a dielectric there. All right, we could fill the space with something else. So whether we put an epsilon or an epsilon naught, I think an epsilon will make more sense because we're thinking of the future where there's going to be a dielectric there. Does that make sense? All right. And that's still going to be E times 2 pi r h. Oh, wait. Well, yeah, I guess so. I mean, I was going to write Gauss's law first, so yay, Gauss's law. And then H over LQ equals epsilon times E times 2 pi r h. I notice immediately that the H's cancel out. That's by design. Next, we're going to solve for the electric field. Made that whole argument about not having a knot on the epsilon, and I threw it in there anyway, so let me fix myself and solve for the electric field. So the electric field here is going to be, we're going to get all this parts together, but it's Q over, a whole bunch of stuff in the bottom here, 2 pi epsilon L R. I think that's everything, right? Now, remember, the electric field for an infinite line was lambda over 2 pi epsilon naught r. do you see that we still have that here? That Q over L is lambda. So it's still the same kind of thing. We didn't have to do all of this because we have this memorized, right? If we don't have this memorized, let's get it memorized, okay? All right, so step 2 is to find the electric, yes, sir. All right, so step 2 is to find the electric field in the region of space between the plates. We've done so. Now we have to find the magnitude of the electric potential. Now, I'm using that word magnitude of electric potential because, let's be very clear here, we don't care whether it's positive or negative. I mean, I could tell you to go from the negative plate to the positive plate, that's fine. But we don't really care, we just want what the electric potential is, not what it, not whether it's positive or negative. But here, if we make the outside plate negative and the inside plate positive, we want to go from B to A. Does that make sense? We all good with that? All right. So I'm just going to leave the electric field on the screen there and write in that electric potential equals minus the integral E dot dr. Scalar product. So we're going to be going from B to A, but the electric field is in the opposite direction. The electric field goes from A to B. So when I start filling this in, my minus sign, going from B to A, Q over 2 pi epsilon naught LR times dr times cosine 180 degrees. Everything good there? Lots of stuffy stuff? All right. Now, let's move that all up there. Cosine 180 is just negative sign. Negative and negative makes positive, so just remove that. Q, 2 pi epsilon and L. Well, I keep putting epsilon naught. It's out of habit, sorry. But 2 pi epsilon L, those are all constants. So I could rewrite this as Q over 2 pi epsilon L integrated from B to A 1 over R dr. Those of you who've had calculus know that this is a special antiderivative. We can't use the polynomial rule because you end up dividing by 0. Those of you who don't know this, you need to come to be acclimated that the antiderivative of 1 over R is the natural log of R. So you need to memorize that, you need to learn it. It's on your equation sheet. You're going to be getting the equation sheets next week. I'm going to just give you yours. I'm not going to give them to you with the test because I'm photocopying them for mechanics this afternoon. Someone's going to make enough for you guys. Some of you will get 2 copies. Good, save them. You lose them like crazy, so save them. Well, not all of you. Some of you probably still have yours from last year. Right, Allie? You're probably the AP Physics 1, though. Not doing you as much good. All right, Q over 2 pi epsilon L. Natural log evaluated from B to A, which Q over 2 pi epsilon L, natural log of B minus natural log of A. Which you should write as the natural log of B divided by A. By definition, B is greater than A. That means this is the natural log of a number greater than 1, which means this is positive. Right? We want to make sure we check our signs because we were trying to be consistent with that kind of stuff. This shows, because we only need the magnitude, but had it worked out to be negative, we would have had to do something to ensure that it's just a positive value. Okay? But that's what we've got. Now, we've done this before, but any questions about this yet? All right, that's step 3. So, of all the things we had to do, remember, this was step 1, step 2, step 3, and now step 4. Put it into our equation for capacitance. So, our equation for capacitance is C equals Q over V. So that's Q over 2 pi epsilon L times the natural log of B over A. We can probably do a little algebra here to clean this up. Of course, the Q's cancel. That's not just by design, but is necessary. And that's going to put 2 pi epsilon L in the numerator and natural log of B over A in the denominator. Now, this is for a cylindrical capacitor. I want to bring back parallel plate capacitor. And I want you to notice something similar here. They don't look at all the same. But if you know a little bit about what to look for here, you'll begin to see some of the things are the same. First, 2 pi is unitless. So if we ignore the units there, the units for this match the unit for that. Because the only thing that's different ultimately is that I have this. That contributes units besides epsilon, and this contributes units besides epsilon. So the natural log of B over A is unitless. So I just have something in meters in the numerator. And for the parallel plate capacitor, I have meters squared divided by meters. So again, I have something that's in terms of meters there. Do you guys see that? You guys follow that argument? Ty does, that's good. Now, when the area of the plates got bigger, the capacitance got bigger. The analogy is that if the length of a cylindrical capacitor gets longer, then the capacitance gets bigger. I think that makes reasonable sense. In this case, the length is a stand-in for the area of the plates. The longer it is, the more overlap you have. The weird thing is, in the parallel plate capacitor, the closer together the plates were, the higher the capacitance. If you'll notice, that's true here too. The closer A is to B, the smaller the natural log is. You follow that? The smaller it is, because if B equals A, the natural log is 0. So that's a limiting factor there. So that means as A gets closer to B, the natural log becomes smaller, capacitance goes up. And that makes sense too. That's the plates getting closer together, isn't it? If you think about it, if B is getting closer to A, that means either the inside's getting bigger and it's getting closer to the outside, or the outside's getting smaller, which is getting closer to the inside. Either way, the two surfaces are getting closer together. You guys follow with that? That's a theme here. Increasing capacitance means more area and closer together plates. That's always going to be the case. So you know you've gotten it right or wrong based on just looking for that. All right, so we have our two. This is parallel plate. And now we have cylindrical. That was a cylindrical capacitor. We did all 4 steps. Ready to try spherical? Go.
Do the bounds have to be from like A on top, B on the bottom?
Okay, so what I had said to do is make your boundaries from the negative plate to the positive plate.
Oh, okay.
So you could go from the inside out if you separate it, but you're supposed to be going, remember, the whole goal is to just have a magnitude anyways, but we want this to be a positive magnitude. If it works out to be negative, you're going to have issues with your calculation later. Does that make sense? Okay. All right. Ready to move along? Because there's more to do. By the way, hit pause. Spherical capacitor. Spherical capacitors are nearly impossible to make. You can make them. The question is why? Why would you? Yeah, I mean, imagine what you have to do. You have to have an inner surface, and then you'd have to have an outer surface that's spherical, like so. But then you'd have to find a way to connect the inner surface to a wire outside of it so you could charge this. So you'd have to like pierce a little hole in it somewhere. I'm not sure exactly how you would do this or even why you would do this, but say you'd make a little hole and then you'd put a wire through there. You know, this would be the only way I think you could do it, right? So then you could have a wire on each side. We don't study spherical capacitances because we make them like this. They're ridiculous when there's so many easier ways to make capacitance. We study spherical capacitors because there are things that are natural capacitors that are spherical and they discharge their energy. The Earth is a spherical capacitor. It discharges stored electric energy into space due to its capacitance, and it collects charge from the sun. So there are reasons to study this. If you happen to have a spaceship and you're out there and the Earth is discharging its electrical energy into space, you could be part of the discharge and that could be bad for you. So there are things that you have to try and kind of do to protect things like that. And although that's a pretty, kind of long and winded way of saying that, yeah, we should study these, the truth is we're not going to make any of these. But let's use the same kind of stuff. Let's have that A, that B. And let's say that we have charged the inner shell to have a capacitance of positive Q, and we've taken that from the outer shell, which has has a charge of negative Q. So step one, we have charged our capacitor. We don't really have to do anything fancy with that. We don't have to find a charge density. Because step two is going to be for us to find the electric field in the region of space between the two spheres. And we already know what that is, right? I don't have to use Gauss's law. If I'm talking about a place right here, then it's just a point charge. So my electric field in that region doesn't require Gauss's law. Now, don't get me wrong. There's no reason why a problem could not ask for you to show by Gauss's law that the electric field is Q over 4 pi epsilon r squared. So if you want me to run through Gauss's law again for this arrangement, I will. Going once, going twice. So we're all pretty okay with that one? All right. So step two, we got the electric field. Step three, we need the electric potential from the outside shell to the inside shell. Again, not much to do here, but don't take this one lightly. The electric potential from the outside shell to the inside shell is going to be V equals minus B to A Q over 4 pi epsilon r squared dr. Now, we've done this, but sorry, I'm chewing. We already know what to expect for electric potential. The issue here is ensuring that what we get here has the right signs and everything, okay? We want it to be positive electric potential. So we're going from B to A. As we travel, we know the electric field is in this direction. We're not going from infinity to A like we do with the point charge. We're going from B to A. That's going to give us the correct cosine, but we need to be careful. We know the electric potential is 4 pi epsilon times R evaluated from B to A, correct? So this is going to give us Q over 4 pi epsilon times 1 over A minus 1 over B. Is that positive or negative? Do you know? I think we know. Think it through. I think we know. Go ahead.
Positive,
How is it positive? How do you know?
because 1 over A would be a larger number since you're dividing by A, which is smaller.
Right. A is smaller, so 1 over A minus 1 over B is going to be positive. All good? All right, so this is our electric potential. We have to place this in the denominator of that fraction. So although this is, step 3, we know that step 4 is going to be to say, all right, my capacitance is going to be Q over V, and that all has to be shoved into the denominator. That's not particularly pleasant. So there is a way to make this a little bit better for us mathematically. And so one way to do that is to get common denominators and add your fraction together. So Q over 4 pi epsilon is going to be B over AB minus A over AB, right? Getting common denominators. Which gives us Q over 4 pi epsilon B minus A over AB. Still positive because B is a greater number than A. You should look into this a little bit, but I want to at least get this expression finished. So Q divided by Q over 4 pi epsilon times B minus A over AB. Q's cancel, and we get this kind of wickedly cool thing. It's A times B over, 4 pi epsilon, A times B over B minus A. The reason I say it's wickedly cool is, look at this. It's meters squared in the top divided by meters. Do you see that? If I make A bigger, B has to get bigger, right? Because B has to be greater than A. So if I make my spheres bigger, I get more and more area, and it's the product of the two surfaces. And there's a 4 pi in there, which gives us kind of surface area. Isn't that kind of weird? It's like average surface area, because it's the small one times the big one. But then the denominator tells us again, if I get them closer together, if I get B and A to be as close as possible, that ramps up the capacitance. So it still follows the same pattern of having surface area on the top and close plates on the bottom.